Hi everyone, I'm Courtney Dressing. I'm an assistant professor of astronomy at the University of California, Berkeley. I wish I could be with you in Pasadena, California for the Sagan Summer Workshop, but I'm excited to be with you virtually to tell you about how we determine the reliability, composition, and stability of transiting planet candidates. In this talk, I'll go over a variety of topics. We'll answer questions like, what are transiting planets, how are they detected, and what planetary characteristics can be determined. We'll then discuss the need for follow-up data and how obtaining additional observations, either from the ground or from space, can help us learn more about planets that we might have discovered. Next, we'll discuss how astronomers figure out what planets are made out of and what we've learned so far about the diversity of planets that are similar in size to the Earth and planets that are even larger than the Earth. At the end of the talk, I'll do a sneak preview about what you might learn in terms of the three-dimensional orientations of planetary systems, but I won't go into too much detail on that topic. There are a lot of words on this slide, so if you want a streamlined view of the talk outline, here it is. We'll start with transiting planets, we'll then go through follow-up observations, then planet compositions, and finally system orientations. To kick things off, let's look at transiting planets. The main goal of this conference is to find planets using the radial velocity method, where you infer the presence of the planet because you see the light from the star Doppler shifted towards you and away from you over time. With the radial velocity method, you're able to measure the mass of the planet relative to the star and the orbital period of the planet. You can also learn things like the eccentricity of the planet's orbit. In this talk, we'll be focusing on the transit method. The transit method is when you look at a star and you monitor how bright the star is over time. If the star has a planet, then that planet might periodically pass in front of the star and block some of the starlight coming from the star. Here you see an actual movie of the sun taken several years ago when the planet Venus crossed in front of the sun. This event was called the transit of Venus, and because both Venus and the sun are close to us, we could see the disk of the sun and the disk of Venus crossing the sun. When we look at stars that are farther away, we're not actually able to see the disk of the star or the disk of the planet. What we can do, though, is monitor how bright the star appears to be. If the star periodically gets fainter for a set amount of time at a particular time, we can then figure out that it has a planet of a given size on a particular orbital period. Here's an animation giving you a closer view about what that looks like. What you see here is a top-down view showing a star with a planet orbiting it. If this were the real configuration of the planetary system, you wouldn't see the transit because the planet would never cross between you and the star. So at the movie's beginning, it will first flip the system such that the planet passes between us and the star. That's required to see a planetary transit. The movie will then record how bright the star appears to be versus time in the lower left corner. When the planet crosses in front of the star, you'll see that the brightness of the star will temporarily be fainter. Here we go. We have the planet orbiting the star in what we call a face-on configuration. Now we flip to an edge-on configuration where transits are possible. We're also starting to monitor the brightness of the star versus time. You can see when the planet was in front of the star, the brightness was a lot lower. If we had a large planet, we'd see a large decrease in brightness. And with a smaller planet, we'd see a smaller decrease in brightness. If the planet proceeded more quickly around the star, the transit event would be shorter in duration, and the orbital period would be shorter in duration. So by measuring the properties of this transit light curve, we can figure out how big the planet is relative to the star and learn something about the planet's orbit. Here's another schematic that helps you figure out exactly what you learn from a planet transit. This is figure 2 from the Transits and Occultations paper by Josh Wynn, which appeared in Sarah Seeger's 2010 Exoplanets textbook. At the end of this talk, I've listed several references that you might want to consult if you're interested in learning more about the topics covered in this discussion. On the top here, you see this disk of the star with a gray circle representing a planet. You see the planet at 4 moments in time as the planet is crossing in front of the disk of the star. Here, these axes are defined, so the center of the star is here, and then you measure the difference between the line that the planet travels on and the center of the star. The distance between where the planet crosses the star and the center of the star is known as the impact parameter, v. If you have a small impact parameter, that means the planet is crossing near the middle of the star, which means the transit will take a longer period of time. If you have a large impact parameter, that means the planet is transiting near the edge of the star, and the transit will take a short period of time because you're only just grazing the disk of the star. On the bottom here, you see a schematic of what the light curve would look like if the planet is at the orientation shown in the above diagram. So on the left here, you see that the light from the star is at a fixed level when the planet is not transiting. And then when the planet first starts to cross onto the disk of the star between moments T1 and T2, the light from the star decreases. And then when the planet crosses the surface of the star between moments T2 and T3, the flux is lower because the planet's blocking the star's surface. Then we have an event called egress between points T3 and T4, where the planet starts to exit the disk of the star. Finally, once the transit concludes, we're back to the normal baseline flux level over here. The number delta here represents how much dimmer the star is during the planetary transit. We can relate this transit depth delta back to the radius of the planet if we know the radius of the star. An important theme to remember for all of exoplanet work is that we only know the properties of the planet as well as we know the properties of the star. So if we want to figure out whether our transiting planet is the size of Earth or the size of Neptune, we really need to know exactly how large our star is. Another quantity we can determine is how long the transit event lasts. The characteristic timescale of a planetary transit is given by this equation here, where here the dominant terms are the radius of the star, the orbital period of the planet, the semi-major axis of the planet. For typical planetary transits, like those found by the NASA Kepler, K2, and TESS missions, you'll be looking at transit durations that are on the order of a couple hours. For a planet that's at a longer orbital period, maybe your transit duration would be 6 to 10 hours. For a planet that's really, really close to the star, maybe it would only be a handful of minutes. And finally, the transit duration itself, T, is represented by this blue line down here. That's the amount of time that the planet spends crossing the disk of the star. And we can relate the transit duration tau, or T, to this characteristic timescale multiplied by the square root of 1 minus b squared. As a reminder, b is the impact parameter. So if your planet is crossing near the center of the star's disk, then the transit will last longer. Whereas if the planet is crossing near the edge of the star's disk, the transit will be much shorter. Another quantity we can measure is tau, which is the ingress and egress duration. Here, the tau is the time between times T1 and T2, which measures the amount of time it takes the disk of the planet to cross onto the star. This is a way of measuring how big the planet is relative to the star. So what you see here is that tau is given by this characteristic time scale divided by 1 minus b squared times rp over r star. So again, you'll need to know the size of the star, and you'll also need to have some guess as to what the impact parameter is. You could fit all of these parameters together using a Monte Carlo Markov chain analysis using your transit data. If you're curious how to do that, I encourage you to check the links at the end of the talk to look back at materials from previous Sagan Summer Workshops. All of this only works, though, if your planet actually transits. And unfortunately, for an Earth-like planet orbiting a Sun-like star, the odds of transit are only 1 in 200. There are just too many geometries where the planet wouldn't appear to pass between you and the star. Here's another figure from the Transits and Occultations chapter to explain why this is true. Here, what you see is the planet on an orbit around the little star. And if we draw out the path of the planet and look at the celestial sphere, what you see is that anywhere along this gray band, an observer would see a planetary transit. But if the observer is positioned above or below the gray band, the planet would not appear to cross in front of the star, and they wouldn't see a transit from that perspective. So here, the purple observer would see a transit, but the green observer would not. Now that you know the mechanics of how transits work and you're able to figure out the properties of a planet from a transit light curve, let's take a look at some of the famous transit surveys of the past and the lessons we've learned from them. Transit surveys initially began from the ground with the discovery of large planets that were Jupiter-sized and extremely close to their stars. You know these as hot Jupiters. More recently, transit surveys have been conducted from space as well, and the main name that you've probably heard from at home is the Kepler survey. Kepler lasted from 2009 to 2013, and it was the successor to the European-led mission Corot. With Kepler, The mission was incredibly successful. They found nearly 5,000 confirmed planets and candidate planets by staring at one patch of the sky for just over 4 years. Here, this artist's rendition shows Kepler in space, staring at a star that's being orbited by a transiting planet. You can look at these numbers in the upper left corner and think about how many planets that must be and how important that must have been for our knowledge of planetary systems. But I find the most effective way to view Kepler's success is to look at a plot of the number of planets known before Kepler and compare it to a plot of the number of planets known after Kepler. So here we go. This figure from NASA shows you the sizes of planets relative to Earth on the left versus the orbital periods of those planets on the bottom. Here the numbers go from 1 to 1,000 days for the orbital period and from 1 to 40 times the radius of the Earth for the planet size. On the top, you'll see that these are non-Kepler discoveries, and in particular, these are all the planets that were known prior to the launch of Kepler in 2009. What you see in the dots are the different positions for these planets, and they're colored based on the way that they were detected. So in pink, we have planets detected via transits. These are primarily planets that are quite large and very close to their stars. In blue, we have planets detected via radial velocity. These planets are also predominantly quite large, and they range from planets that are close to their stars all the way out to planets that have orbital periods of several years. We also have some imaging discoveries, some microlensing discoveries. Here's a point right here, and then 2 planets here that were detected via the pulsar timing method. You can learn more about all of these planets by browsing the wonderful resources on the NASA Exoplanet Archive. So this was the landscape pre-Kepler. We had lots and lots of big Jupiter-sized planets, a handful of planets here in the middle that were roughly the size of Neptune, and pretty much nothing down in the lower part of the plot where this line represents planets that have the same radius as the Earth. After Kepler, though, the plot looks like this. Just in case you missed it, I'll flip back. This is before Kepler, after Kepler. Before, after. All of these yellow dots are planets that were found by the Kepler mission. They range in size from planets that are smaller than the Earth all the way up to planets that are so large that they're probably actually astrophysical false positives. And they range in orbital period from objects that have periods less than a day out to objects that have periods of a couple of years. Looking at this plot, it really shows that the Kepler mission has changed fundamentally our understanding of planetary systems. It's demonstrated that small planets are common and that there are types of planets in the universe that are totally unlike those in our own solar system. I find it even more remarkable to remember that all of these yellow dots are in this tiny patch of the sky. Here, these rectangles show you the Kepler field of view, which is visible in the northern sky in the summer near the constellation Cygnus the Swan. With Kepler, the mission stared at about 100,000 to 100 to 200,000 stars in this patch of the sky for multiple years. It recorded the brightness of those stars every 30 minutes and monitored to see which of those stars might be orbited by transiting planets. Kepler had the ability to detect thousands of planets orbiting these stars, but it only looked at this patch of stars. Later on, after the end of the main mission, Kepler was transformed into the K2 mission, and then it surveyed fields along the ecliptic plane, finding more planets orbiting stars with a variety of ages and metallicities. But Kepler and K2 combined only looked at a small fraction of the sky, and it would be really wonderful to know about all of the transiting planets in the sky. So fortunately, recently, on April 18th, 2018, NASA's Transiting Exoplanet Survey satellite, TESS, launched into space to begin an all-sky survey for transiting planets orbiting nearby bright stars. TESS is looking at very bright stars because we want to find planets that we can characterize and understand in detail. The planets found by TESS are ideal targets for radial velocity studies, just like the ones you're learning about at this year's Sagan Summer Workshop. For comparison, this figure from Zach Britta Thompson shows you the search space for the TESS mission compared to the NASA Kepler mission. The yellow cone here shows you that Kepler looked for planets around stars that were medium distance away, about 3,000 light years away, and it was looking at a tiny little sliver of the sky. Kepler adopted an approach that's similar to what's called a pencil beam survey. So it looked in one direction and found everything it could find along that direction. In contrast, TESS is looking at stars that are much closer to the Earth, but it's looking for them in nearly all directions. So with TESS, we'll find the best set of planets possible for future study with transit work with the James Webb Space Telescope to study planetary atmospheres, or with ground-based radial velocities to study planet compositions. TESS is a game changer when it comes to finding planets around nearby bright stars that are perfect for detailed characterization. So let's look at the highlights of TESS, and then I'll show you one caveat that explains the rest of today's talk. One of the things we can do with TESS is if we have a planet orbiting a bright star, we can figure out what that planet's interior structure might be by measuring both the mass and the radius. We'll get to that later today. With TESS, we can also study the atmospheres of planets by looking at the planet as it crosses in front of the star's surface, and instead of just taking photometry, instead using a spectrograph to split the light up into a rainbow and trying to determine what molecules might be present in the atmosphere of the planet. I'm not going to discuss that in detail today, but you can find previous talks about atmospheric spectroscopy in previous summer Sagan workshops. When you have the full sample of planets found by TESS, K2, and Kepler, you can also investigate the demographics of planetary populations. This is a little bit risky because there are many selection effects that come into play here in terms of which stars are observed when and the likelihood of detecting planets. But once you correct for those effects, you can do interesting work to try to figure out exactly why the planetary systems appear the way they do and why certain types of stars might have certain types of planets. The big catch with all of this, though, is that when TESS is looking at stars and recording how bright those stars might be, the mission itself might find some objects that are not actually transiting planets. So some transit-like events, some decreases in the brightness of the star, will be caused by planets crossing in front of the star, but others won't be. In some cases, the system might look like this. We could have a star orbited by a planet, and when the planet crosses in front, the system will look dimmer. In other cases, though, we might have configurations like the ones on the upper right or the lower panels. We could have a small star passing in front of a big star. We could have a stellar binary that's close to another star, such that when the two stars eclipse each other, the light from the other star close by is diluting the depth of the eclipse, causing us to think we're seeing a small decrease in brightness when really we're seeing a large decrease in brightness. Or we could have a case where we have two roughly similar sized stars that are just barely grazing each other. So they're just slightly touching at the edges when they eclipse in a projection view, and that causes us to see a small decrease in brightness. Fortunately, there are clues in the TESS photometry that might help us figure out that we're seeing these types of false positives rather than a real transiting planet, but it's tricky. It's doubly tricky because TESS has extremely large pixels. Kepler had pixels that are about 4 arcseconds on a side, but TESS's pixels are over 20 arcseconds on a side. And there can be a lot of stars within 20 arcseconds. So it's important, before investing lots of valuable resources to measure the mass of a planet with TESS, to try to figure out which of these potential transit-like signals are real planets and which of them are astrophysical false positives. If you've read a lot about Kepler and how they did this during the Kepler era, you've probably heard about Blender, developed by Francois Bresson, and Pastis, and Tim Morton's Vespa code. All of these packages were necessary to look at the large set of Kepler planet candidates and make educated guesses as to which of them were most likely to be real planets, based on the morphology of the transit light curve and the available follow-up observations at that time. For the TESS era, there are a couple of differences between how TESS works and how Kepler works. So one of the graduate students in my research group, Stephen Jackalone, has been developing the Triceratops pipeline, which allows him to look at TESS photometry and try to figure out which planets are likely planets and which ones are likely false positives. Triceratops works in a complementary fashion to Vespa because Triceratops has an added ability to look for nearby eclipsing binaries. So when you're looking at TESS candidates and trying to figure out which ones are real and which ones are false positives, I encourage you to check out multiple packages, including both Vespa and Triceratops, to try to make your own estimates as to which ones are real and which ones are not. A helpful ingredient as you inspect the veracity of TESS planet candidates would be to include follow-up observations. If you've been following along with the TESS mission, You've probably heard about TFOP. TFOP stands for the Test Follow-Up Observing Program, and they have the goal of doing all of the precursor observations required so that they can measure the masses of 50 planets to a precision to a sufficient precision so they can determine what those planets might be made out of. And on their way to determining the masses of these planets, they have a flow chart for how they'll get to that point. So with tests, we get light curves for hundreds of thousands of stars. Those light curves are then inspected to see which of them contain transit-like signals. And on this early diagram from the test planning days right before launch, they expected to find something like 3,000 signals for transit-like events. They would then look at those signals in detail by conducting imaging to try to figure out which signals were associated with the target star, which ones were associated with nearby stars. So maybe that would rule out 500 or so false positives. Next, they would use spectroscopy to try to figure out whether any of these systems were spectroscopic binaries rather than transiting planets. Maybe at that stage, you'd keep something like 1,700 candidates. Next, you'd start performing detailed radial velocity work to measure the masses of planets. And here, that's a big down select because they're also looking for things like which planets are expected to have measurable signals, which stars have sufficiently slow rotation periods, which stars are not very active, all sorts of cuts that you've heard about in your other talks for this summer workshop series. And then in the end, the goal for the level 1 science requirement for the test mission is to measure the masses of 50 planets with radii smaller than 4 Earth radii. So they want to define 50 planets smaller than Neptune and determine what their masses are, and therefore what their bulk compositions might be. In order to make all of these observations possible, they've organized the Test Follow-Up Observing Program. This graphic is probably a little bit small on your computer screens, so we'll break it down in the series of following slides. TESS, TFOP, is divided into multiple working groups that allow them to pursue different types of follow-up observations designed to rule out false positives. The first of those subgroups is the Scene Limit Imaging Group. This group contains many amateur astronomers who use backyard telescopes to observe planetary transits, in many cases to observe stars that might actually be eclipsing binaries, and then report their observations online to share them with the community. With a small telescope in your backyard, you can't get the same resolution that you would with the Hubble Space Telescope, but you can still get enough resolution in order to produce a higher resolution view than what you would have had with TESS's large 20 by 20 arcsecond pixels. With your backyard telescope as a subgroup 1 member, or perhaps with your university telescope or a medium class telescope, what you would do is you would take transit photometry and measure the brightnesses of multiple targets within the field of view. Over the course of the night, you would determine whether any of the stars in the field showed a transit at the expected time, and then you would figure out whether the star that showed the transit was the target star or whether you were actually seeing a nearby eclipsing binary. In some cases, if you have sufficient aperture and sufficiently stable conditions, you might be able to precisely determine the time at which the transit occurs and to measure whether there are any deviations from the expected transit time. These transit timing variations provide a way to measure the mass of a planet due to gravitational perturbations from planets in multi-planet systems. So that's subgroup 1. The next subgroup is subgroup 2, which performs reconnaissance spectroscopy. In this case, what they're doing is they're picking out a particular star that's suspected to host a candidate transiting planet, and they're acquiring a couple stellar radial velocities. These are low precision radial velocities, and in this case, what they can do with the spectroscopy is to figure out what the stellar parameters are. They can determine what the effective temperature is, what the surface gravity is, and what the metallicity is. So this is a way to figure out whether you're looking at a main sequence sun-like G star or whether you're looking at an evolved star. You can also figure out whether you're looking at a star that seems interestingly metal poor or metal rich. In some cases, once you acquire multiple radial velocities at different phases for the planet, you might also find that the planet is really a spectroscopic binary. But if it's not, your improved stellar parameters will allow you to refine your estimate of the planet properties because you'll need to know the stellar radius in order to get a good estimate for the planet radius. And if you're able to determine the temperature and the surface gravity of the star, you could then get a better estimate of the mass and the radius of the star. Another thing you can do with the subgroup 2 reconnaissance spectroscopy is to estimate what the stellar rotation rate might be. This matters because if you find an extremely rapidly rotating star, it would probably be a challenging target for future precise radial velocity work, and therefore would be a bad candidate for mass measurement. Subgroup 3 is devoted to high resolution imaging. This differs from subgroup 1 because you're doing something to try to reduce atmospheric turbulence on your observations. With subgroup 3, you obtain images at even higher resolution than subgroup 1 does, and you're able to detect stellar companions that are even closer to the star. So in this case, you might be detecting companions that are even less than an arcsecond away from the target star. These would be completely blended in the test photometry, so you wouldn't be able to tell that the other star was there without acquiring this subgroup 3 high-resolution imaging. Having these images allows you to figure out whether a stellar companion is present, and if it is present, you can then correct for the dilution caused by the light from that additional star and refine the estimate of the planet properties. So if you detect that there is a star close to the target star, that would probably mean that the planet you thought was, say, Earth-sized is actually Neptune-sized. You can also determine whether the star that you've detected is likely to be physically associated with the target star, or if it's just a chance alignment, or maybe your target star is 30 parsecs away and the other star is a background star at a distance of 300 parsecs. You can use multiple techniques to obtain these high-resolution images, but the common ones include adaptive optics imaging, speckle imaging, and lucky imaging. You can learn more about all of these techniques by looking at the slides from previous Sagan Summer Workshops. In particular, you'll want to check out the transit follow-up slides from what I think is the 2016 workshop. We were looking at a lot of lists for what the subgroups do. So as a quick refresher, let's take a look at some of the work done by subgroup 3. Here, what you see is an image in declination versus right ascension space of a planet candidate host star known as TOI, or Test Object of Interest 13901. In this case, what you see is that it's just a single point of light. So that tells us that this star is on its own. In contrast, this next star, TOI 123, has another star nearby. So this could be evidence that maybe this transiting planet is less believable than TOI 13901. But it's important to actually figure out what the presence of the additional star does to the transit interpretation. In many cases, you can have a star close to the target star and still have a transiting planet. It's just that the transiting planet is slightly larger than you might have suspected initially. For fun, I also wanted to throw in this slide, which shows a series of images that were collected and reduced by Arden Zabel, who is a recent graduate of UC Berkeley and is just about to start grad school at the University of Maryland. What you see here are the diversity of stellar projected binaries that we found while trying to screen Kepler target stars to identify which stars were single and which stars were in stellar binaries. Collaborators on this project include Jesse Christensen and David Chiardi. You've probably seen multiple times during this workshop already. Moving back to the test subgroups, subgroup 5, and yes, I know I skipped subgroup 4, but there's a reason for that. Subgroup 5 is space-based photometry. This subgroup obtains high cadence observations of the target star and registers exactly how bright it is during a suspected transit event. So if you found a planet with an orbital period of 7 days, you would figure out that the planet is next going to transit on, say, July 23rd, 2020, and you'd request time to look at the star at that time and figure out whether the transit occurred. And if it did occur, measure exactly when the transit ingress and egress occur. By taking these data, you can improve estimates of planetary properties by more precisely measuring the transit depth, which gives you the planet radius, and also the transit duration, which tells you more about what the planet orbital period might be. If you detect transit timing variations, that could also tell you that there's another planet in the system, and then you could try to figure out what the mass and the orbital period of that planet might be. Conducting these observations is possible with a range of facilities. The most common suspects used to be Spitzer and Hubble Space Telescope, but as we go towards the future, you'll see more of these observations hopefully made with James Webb in the future. Finally, the last subgroup is subgroup 4, which is precise radial velocity. I saved this one for last because it's the topic of this year's Sagan Summer Workshop. With Subgroup 4, you'll be obtaining spectra of the star using an extremely precise spectrograph in order to determine exactly what the semi-amplitude induced by the planet is, which will allow you to determine the planet mass and hopefully constrain the planet eccentricity as well. Along the way, you might discover other planets in the system, which would teach you more about the planet architectures and configuration. Once you have that planet mass from the precise radial velocity follow-up, we can then consider what the planet composition might be. If we look at our own solar system, we see that there are two flavors of planets. Close to the sun, we have all of these small rocky planets. This includes Earth, Venus, Mercury, and Mars. Farther away from the sun, we have large gas and ice-rich giant planets. This is extremely orderly and might cause you to assume that all planetary systems look like this. They have small planets on one side, they have a nice dividing asteroid belt, and they have large planets. That's a nice picture, but unfortunately, or fortunately, it's not true. Many other planetary systems have a more jumbled-like appearance, and it's not as easy to predict what another planetary system might look like. Moreover, if we look at the size distribution of planets orbiting other stars, what we see is that there are many planets with sizes intermediate between those of the small planets in the solar system and those of the large planets. This 2013 figure from Andrew Howard's science paper shows you the number of planets per star as a function of the planet size relative to Earth. On the left, we go from 1 Earth radius, and then on the right, we actually have planets that are about twice the size of Jupiter. You can see right away that the small planets are more common than the large planets, but you might also be perplexed to see all of these planets shaded in yellow at sizes that don't exist in the solar system. This early view has evolved over time as we've gotten better measurements of the stellar radii, and of course, from the stellar radii, better measurements of the planet radii. In this 2018 figure, this is corrected for the frequency of planets, accounting for the fact that not all planets transit and not all planets are equally detectable. What you see are the number of planets per star with orbital periods less than 100 days as a function of planet size. And if you trace the black line, you can see that planets that are roughly Earth-sized are quite common. Then there's a deficit of planets around 1.8 to 2.4 Earth radii, and then you have a lot of planets around here. And then if you go to even larger sizes, the number of planets declines again. So as you look at this plot, you might be interested in what's causing the change between these small planets and the large planets. And it seems to be that the effects from over time from the stellar radiation are causing the atmospheres of some planets to photoevaporate away. An alternative theory is that perhaps it's difficult to form planets that fall within this gap here. If you'd like to know more about this, you should go and look at the Fulton and Pettigrew paper, as well as the papers that followed, and the associated theoretical papers by James Owen and Eric Lopez. If we look at a planet and we only measure the planet size, it's difficult to tell what the planet might be made out of. Here, I'm showing a very rough schematic that shows that I'm most definitely not an artist. On the left, you see a schematic where you just have a gray ball surrounded by a thin blue line, representing a planet that's probably rocky. On the right, you have a small gray ball and a big puffy blue atmosphere, representing a planet that is rich in volatiles, things like water, hydrogen, and helium. If you only have the radius measurement, you can't distinguish between these two possibilities. But if you measure the mass, then you could determine the density and try to figure out what the planet might be made out of. So to do this, we can remember that density is equal to mass divided by volume. We can get a mass from the radial velocity method, or we could use the transit timing variation method. And we can get the radius from the transit method. When we put those two things together, we can then estimate what the interior composition of the planet might be. To guide us, let's go back to the solar system again. Here we have the terrestrial planets of the solar system. They're in order, but they're squashed together way too close. Earth you recognize, and Earth is 1 Earth mass and 1 Earth radius by definition. Our sister planet Venus is a little bit smaller and a little bit less massive. On the right side of Earth, we have Mars, which is about half the radius of Earth, but significantly less massive. and Mars has a smaller iron core for its size than the Earth does. In contrast, Mercury is actually more iron-rich than one would expect. So in the solar system, if we were to cut all of these planets up and look at the interior, we'd see that they all look vaguely similar. They all have cores and mantles and crusts, but the fraction of the planet that's spent in the core versus the mantle is different from one planet to another. So that tells us that we know some things about terrestrial planets, but the details might be harder to predict. If we go to the outer solar system and we look at the small bodies out there, and in particular, if we look at the large moons in the outer solar system, what we find is that we also see cores and mantles and crusts, but in these cases, we're actually looking at icy shells and water mantles because the building blocks in the outer solar system are different from the building blocks in the inner solar system. This tells us that if we find a planet around another star, it might require more knowledge of what kind of material was present for the planet to form from in order for us to figure out how the mass and the radius, which are only two measurements, map to a detailed interior structure. In a framework established by Carolyn Dorn, you can imagine that you have a generic planet where you have a core, a mantle, an ice and ocean layer, and then a gas layer. If you only have two constraints, you have the mass of the planet and the radius of the planet, you could make the core really tiny and the mantle really big, and then you could do something with the ice layer and the ocean layer and the gas layer, but there would be multiple configurations that could reproduce both the radius and the mass. So we need as much information as possible in order to explain what the planet looks like. One thing you could do is look at the composition of the star and try to infer what the material would have been present in the protoplanetary disk at the location where the planet exists. But then you would also want to do things like correct for planet migration and consider exactly how the planet formed over time. So it's a fascinating problem, and it's a rich area of research today. Once you've decided how thick each of these layers are, you'll then use physics to try to figure out how the planet would appear. So in general, if you have a large amount of high density materials, things like iron, for instance, that would set the mass of the planet. So if you really pump up the amount of iron, you get a bigger core, and that causes your planet to be more massive. If you have a larger amount of low density materials, that wouldn't change the mass of the planet too much, but it would cause the planet to appear significantly puffier. So you could imagine that the mass is driven by high density materials and the radius is driven by low density materials. If you want to get a little bit more technical, you could click on the link here to read the paper by Carolyn Dorn, which is in one of the exoplanet textbooks that I've linked at the end of this presentation. And then you would find that you can solve for the interior structure of the planet using the equations of mass conservation, hydrostatic equilibrium, and the equation of state. These equations might look familiar from some of your astro classes, and if they don't look familiar yet, you'll probably see them as you take more classes this fall. You could use these equations then to figure out what the radius of a planet would be at a given mass and composition. Here, you can see figures showing model tracks for different recipes for how you build a planet. So on the left, you're looking at the radius of the planet, and on the bottom, you're looking at the mass of the planet. Both of these are relative to the Earth. Each of the colored lines shows a planet with a different composition. In red, you have a planet that's made of pure iron, which is quite unrealistic. We wouldn't expect to find a ball of pure iron floating around in space that's the size of the Earth. And then in yellow, you have a planet that's pure magnesium silicate. So you think of that as like a pure chunk of the Earth mantle. Then in dark blue, you have a planet that has some water ice and some iron. And then in light blue, you have a planet that has some magnesium silicate and some water ice. These are just mock compositions to tell you what kind of intuition you should have for a planet with that radius and mass. But you could imagine building a more complicated model that includes a whole bunch of different layers based on your expectations for how planets should form. If we add on the planets with precisely measured masses and radii to this plot, those are shown here by the points with the error bars. And you can see that they fall into two groups. There are some planets that are down here near Kepler 60, Kepler 21b, Kepler 10b, HIP 219134c. All of these planets appear to be clustering along the yellow line. That yellow line also runs close to these two dots down here, which represent Venus and the Earth. So what this tells us is that the small planets seem to have compositions that are roughly similar to that of the Earth. In contrast, in the upper right of the diagram, we see planets like GJ 1214b and Kepler 11b. These planets lie above the blue lines, so that indicates that they have to have a significant amount of volatiles like water, hydrogen, or helium to explain their compositions. They're just too puffy to be made of Earth-like materials and have the masses that we measure. So you can see here a divide between what's conventionally called the super-Earth population and what's called the mini-Neptune population. This picture looks nice and neat, and it explains the dip we saw earlier when we looked at the planet radius distribution. But don't get too comfortable, because all of these planets are highly irradiated. So that means we haven't quite figured out everything yet. This sample of planets is dominated by planets that have extremely short orbital periods. And we know that there are lots of planets that are farther away from their stars and therefore might have different irradiation histories. If a planet didn't grow up looking like this, then it might have a different composition today than a planet that was sandblasted from the early days of its life. So really, if we want to understand the full compositional diversity of planets, we want to measure the masses and the radii of planets at a wide range of orbital periods and installation fluxes. You might now be wondering why we haven't done that already. After all, on that Kepler slide, I showed you thousands of transiting planets found by Kepler. And that was a while ago. So why haven't we measured the masses for all of them? Turns out it's because many of those planets orbit extremely faint stars. This histogram shows you the brightness in Kepler magnitude, which is similar to V magnitude, for planet candidates found by Kepler. And you can see that it goes from relatively bright stars with magnitudes of 7.5 to 10 to 12, all the way to faint stars. And there's a giant drop off right here because then they got kind of faint and people didn't want to target them with Kepler anymore. But now I'm going to show you which of these targets are good targets for current radial velocity instruments. And I want you to make a guess where that line will be. Will it be over here, over here? Turns out it's there. Only 9% of the sample orbit stars that are bright enough that they're good targets for high-res on Keck, which is one of the instruments that was used for a lot of Kepler mass measurement follow-up. This is why we don't have a mass radius diagram that's filled out to have 100,000 planets on it. We also don't have 100,000 transiting planets. But if all of these planets that we detected with Kepler orbited stars that were brighter than, say, 11th magnitude, then we would have more information about how the masses and radii of planets change as a function of orbital period and installation flux. You also know from hearing the radial velocity talks that there are a lot of challenges associated with measuring the masses of planets, and that as you go out to longer and longer orbital periods, the problem gets trickier and trickier. Fortunately, though, TESS is providing lots of hope for this effort to determine planet compositions because TESS's targets are significantly brighter than Kepler's. TESS is actually such a great tool for finding radial velocity planets that all of these facilities have either come online recently or will come online with the goal of measuring the masses of TESS planets. We'll then be able to add many more dots to the mass radius diagram and really uncover what is driving the compositional diversity that we see at different planet masses and installation fluxes. To give you a picture for what things look like today, this plot from the Exoplanet Science Strategy Report prepared for the National Academy of Sciences shows that we're actually pretty far from measuring the properties of planets that are like those in our own solar system. On the left, you're looking at the planet mass versus orbital period, and on the right, you're looking at planet radius versus orbital period. In both panels, the red dots represent the planets in our own solar system, and the small colored dots represent planets orbiting other stars detected by a variety of methods. For instance, in blue, you see the planets that were found with with transit on the left panel. These are the transiting planets. And then on green, you see the planets that were found with Kepler in transit. And what you notice is that there's actually a big difference between where these exoplanets are and where the solar system planets are. And even more horrifyingly, many of the dots that appear on the left diagram as planets that have a mass and an orbital period don't actually have a measured radius. and many of the planets that have measured radii don't have many measured masses. So this means that we have a lot of work to do in order to fill out the diagram and complete the picture of how planet composition varies as a function of stellar properties and planetary insolation. As we look towards the future, the WFIRST mission, which will launch after the James Webb Space Telescope, will push us out towards longer orbital periods and fill in what we know about the occurrence of planets at cooler temperatures. Here, what you see is a search space for WFIRST compared to the search space for Kepler. Here on the left, we have the planet mass and Earth masses, and on the bottom, we have the semi-major axis in astronomical units. The red dots are planets found by Kepler, and the blue dots are simulated detections of planets found by WFIRST. The symbols here, the little graphics, show you the planets in the solar system. And what you see is that with WFIRST, we'll finally be tracing down to find planets that have masses and semi-major axes similar to those in the solar system. Unfortunately, though, we won't get the radii of these objects, so we won't be able to do the compositional work. We will, though, be able to look at the overall trends in how common these planets are. And then hopefully we can put that together with what we learn from combining radial velocity observations with transit observations in the near term. Finally, for the last chunk of the talk, I promised that I would discuss a little bit about the three-dimensional orientations of planetary systems. First, I wanted to remind you that stars aren't just stationary, they're spinning. And as the planet orbits the star itself is spinning on its rotational axis. So here, you have a little cartoon of a star that's spinning around in this direction, and the black dot represents a planet. As the planet orbits the star, it'll cross over the part of the star that's rotating towards us, and it'll cross over the part of the star that's rotating away from us. So in this figure here, what you see are 3 different rows and 3 different columns. So let's start off with just looking at the left column first. On the top left, you're looking at a plot of how bright the star is, that's shown in the yellow, and you can see that the star is spinning and the planet's in the lower left. And then if you look on the panel right below that, the star has been colored in blue and red to indicate the Doppler shift from the star. On the left side, we see that the star appears to be blue because the star's surface is moving towards us on that side. And on the right side, the stellar surface appears to be red because the star is moving away from us. On the bottom, we're looking at the line profile, which is telling us how the star's overall radial velocity signature is affected by the presence of a planet. On the left side here, there's a little divot, and that's because this planet is blocking part of the blue part of the star, which means it's blocking some of the light that is blue shifted. On the middle panel, the planet has moved to be in the middle of the star, and it's lying on the part of the star that doesn't seem to be moving towards us or away from us. So it's blocking at the center of the line on the bottom. And then on the right panel, the planet's on the right side of the star. It's lying on top of the red surface, which is part of the star that's moving away from us. And then we see that there's a little divot in the lower right part of the diagram, indicating that we're missing some of the flux that would be redshifted. This blue arrow here indicates that we would then measure an overall blue shift in the stellar spectrum. In contrast, on the lower left panel, the red arrow indicated that we would measure an overall redshift in the stellar spectrum. Here, this is just 3 snapshots in the movement of the star across the planet, but you could imagine that we would take spectra of the star throughout the entire planetary transit. We would then be able to figure out the path that the planet took across the star. So here, you see 3 different views of planets transiting spinning stars. In all cases, the stellar rotation axis is pointed up to the top of the page. And then this line shows you the direction of travel of the planet across the star's surface. We'll start off with the left panel. Here, the star is spinning towards us on the left, away from us on the right. And you can see that the planet first starts blocking off some of the light here, and then over here. And that causes us to see the shift going towards positive RVs in the top, then neutral in the middle, then negative RVs at the bottom. In the middle panel, we're cutting across the star at an angle. So we see something that looks less symmetric. We have a small deviation towards positive signals on the top, and then a larger deviation towards negative signals on the bottom. And then finally, on the third panel, we're not cutting across the left side of the star at all. we're only cutting across one half of the star. So here, we only see the deviation towards negative radial velocities, and we're not seeing the positive signal at all. So this technique, which is taking advantage of the Rossiter-McLaughlin effect, allows us to measure the sky projection angle between the planet's orbit and the stellar spin axis. We care about this because if we figure out how a planetary system looks today, we can try to explain how it might have gotten that way. We might expect over time that a planet would be oriented so that it's spinning around in the same way that the star turns. We might also expect the planet should form that way because of the conservation of angular momentum. But when we look at planetary systems, we see that some of them look to be flat and coplanar and aligned with the stellar spin axis, while other systems have planets that transit at angles like the ones shown here. And that mystery allows us to try to figure out exactly what happened to those planetary systems early on. And it allows us to figure out what role other planets and perhaps other stars in the system might have. We're now going to wrap up and look at all of 4 topics we talked about today. I promised that we'd go over transiting planets, follow-up observations, planet compositions, and system orientations. We did all of those things, and I encourage you to do more reading following the links at the end of this slide deck. But to give you just the Cliff Notes version of today's talk, for transiting planets, we learned that those are planets that cross in front of their stars as seen by the observer. We detect them by monitoring how bright the star appears to be. If the star gets dimmer every 5 days, we know that the planet has an orbital period of 5 days. If the star gets a lot dimmer, we know the planet is relatively large compared to the star. But if the star only gets a little bit dimmer, then we know that the planet is relatively small. We also discussed the importance of follow-up data for figuring out which candidate planets are real planets and which ones are astrophysical false positives. We learned that if we have seen limited imaging, we can try to screen out nearby eclipsing binaries that might look like planets. If we have reconnaissance spectroscopy, we can identify spectroscopic binaries, which are ones where you see that the radial velocity signal is changing by way too much for that to be a planet. And we could also get information about the stellar temperature, surface gravity, and metallicity that would allow us to improve our understanding of the planet properties. With high-resolution imaging, we can identify nearby stars that could be diluting the transit depth of transiting planets, or even causing eclipsing binaries to appear to be transiting planets. With space-based imaging, we can get better constraints on exactly when future transits occur, which would allow us to schedule detailed atmospheric studies, for instance, with the James Webb Space Telescope. And finally, with precise RVs, we can determine planet masses, which allows us to constrain planet compositions. We also discussed planet compositions and learned that we can measure both planet masses and radii to get a constraint on the bulk density of the planet, but that we have too many free parameters to uniquely determine what the interior structure of the planet might be. We can get the radius from the transit light curves. We can get the masses from either radial velocity or transit timing variations. For more information on transit timing variations, check the previous Sagan Workshop's talk schedules. We also learned that if we look at the overall distribution of planet compositions known today, small planets tend to have higher densities that are consistent with Earth-like compositions, whereas larger planets require more volatiles like water, hydrogen, and helium. We also know now that most planets with compositional constraints are really unlike the Earth. They're either a lot hotter or a lot more massive, and in many cases, they're both hotter and more massive than the Earth is. So we still have work to do in order to measure the masses of smaller and cooler planets. Finally, we touched briefly on three-dimensional orientations of planetary systems and learned that the Rossiter-McLaughlin effect can allow us to measure the orientation of the planet orbit relative to the stellar spin axis. We know that some planets have orbits aligned with the spin axis of their host star, whereas other planets spin in the opposite direction or at intermediate angles in between. Finally, if you'd like more references, I encourage you to check out these previous Sagan Summer Workshops. You can find the PowerPoints of the presentation. You can also find the videos of some of the talks and even sometimes the exercises that were conducted during the workshop. I also recommend checking out these textbooks. If you don't want to pay for them, this second book in particular is quite expensive. Check out the university library website for your home institution because often those textbooks are freely available in the online version. You can just download the chapters and read them at your leisure. And then finally, I also have a couple journal articles here and a few websites that you might find interesting. Thank you very much for your attention, and I'm looking forward to talking to you later on in July at the workshop itself. Have a good night.